Okay, a few people are still joining us, but I think it's time to get started. So welcome back. And we'll now have the talk by Huang. He will tell us about spinning the X-tail.
Okay, thank you very much for the invitation to talk here. So I'll discuss some recent work and as well as upcoming results that was done in collaboration with Ming Zizhen, my PhD student, Junwoo Kim, Samin Lee from Seoul National, Nima, Donald, Uriko from NYU, Wei-Min Chen from Amsterdam, and Bo-Ting Chen and Man-Kwon Tam are the new students that have just joined the group. So the no-hair theorem basically tells us that black hole is characterized by the three quantum numbers, the mass, the charge, and the spin. Now, these quantum numbers are the same quantum numbers that you will use to characterize an elementary particle. So it's natural to ask, to which extent can black holes be described as elementary particles? Now, if we think about things that are far away, then naively, this statement seems to be empty because anything looks like a point particle far away. But of course, the devil is in the detail. Because if you want to talk about a point particle, you would go to, for example, a world line description. And once you do that, you'll realize that you can have these these higher dimension operators. For example, for a spinless particle, sorry, I can't seem to get my pointer. Okay, never mind. So there are these Wilson coefficients, these higher dimension operators where I've listed for the spinless case. And these E's and the B's are the electric and the magnetic part of the Riemann tensor. So for example, in this case, the Wilson coefficients corresponds to the tidal love numbers, which basically describes how the black hole stretches or the compact object stretches in external gravitational field. So this number would be 0 for a black hole, but non-zero for a neutron star. So there will be a distinction. If we now let the object to carry spin, the story becomes much more interesting because even at linear order in Riemann tensor, you have infinite number of higher dimension operators, with each with their own Wilson coefficients. So these are the different spin multiple moments. If we're talking about a spinning black hole, then these Wilson coefficients are set to 1, which you can derive by looking at the Kerr metric and then expand to first order in G and to all orders and spin and do the matching. So what we like to ask is, what is the on-shell statement of C equals to 1? Or in other words, what is the on-shell statement of the no-hair theorem? And furthermore, since in 4 dimension, we know that there's really a lot of distinct black hole solutions. So how does these different black hole-like solutions actually differentiate among them in this on-shell language? And finally, if possible, we want to explore what are the possible physical principles that select these coefficients. So to answer that, we go from the world line to something on the world line theory to something on shell. We can take all of these world line operators and then let's just sandwich it between polarization tensor, and then we all get a scattering amplitude. So the scattering amplitude, the possible 3-point scattering amplitude now encodes all the possible distinct Wilson coefficients. Since we're talking about massive scattering amplitudes, so they naturally transform under the irreducible representation of the SU2 massive little group. And so we would like to have a formalism that manifests this feature. And of course, since now p squared is no longer 0, we have that ready for us. The p is now a rank 2, oh, great, it's back. So the p is the rank 2 2x2 matrix, so it has 2 eigenvectors. These 2 eigenvectors now form the doublet under this SU2. So for example, for something that has a spin S state, then it has the 2S symmetric SU2 indices. And these indices are naturally carried by these massive little group spinners, these massive spinners. So we can factor them out, which are basically the on-shell version of factoring out the polarization tensors. And what is left behind is just a 2S symmetric SL2C tensor here. So in other words, for the 3-point amplitude that we're looking at a spin S, and a massless particle. The tensor structure we'll be interested in is a 2S times 2S symmetric tensor in the SL2C space. So to explore the possible structures in this space, we need a vector to span that space. And then a natural kinematic vector would be the massless spinner for the massive momentum. Now we have, so that will be one direction, and the other direction will be orthogonal to that, which just means that we need to introduce the Levi-Civita tensor. Now, importantly, which is the main character in this story, is that because of the degenerate kinematics, the lambda 3 here is actually proportional to lambda 3 tilde. And so we're going to define this x as the proportionality factor. So x is essentially defined kinematically in this fashion. And of course, this only makes sense, this doesn't make sense in Minkowski signature. You either have to go to complex or 2-2 signature, whose space-time interpretation Donald has briefly mentioned in the previous talk. So the 3-point amplitude is now just constructed out of just x, lambda, and the Levi-Civita tensor. And so in general, for spin s, you would have 2s plus 1 structures. So I've listed, for example, for spin 1/2, you have 2. For spin 1, you have 3 possible structure. And so this basis is defined purely kinematically. So this is purely on shell, which means that the different interactions has a special unique feature to it. So for example, for minimal coupling, for s equals 1/2, QED is just x times epsilon alpha beta. It's just that simple. For the usual, what we talk about, the g-2 is already automatically separated out. It's this x times lambda lambda. For s equals to 1, you have the g-2. You also have the g-2 for the dipole moment, but because you have spin 1, now you can have quadruple moments. And so everything is nicely separated. Okay, so now we have this on-shell parameterization of the possible 3-point amplitudes. Once you stare at it, the natural question to ask is, what if I just set all the g's to be 0? So in other words, what corresponds to the simplest scattering amplitude, which is just x and everything else is just the epsilon 2s. So if it's coupling to, if it's electrically charged, then it will be just x, and if it's gravitational coupled, it will be x squared. You can, instead of looking at this, you can also look at the second one, which is basically just contracting the external polarization tensors. Now, what will correspond? Is there anything in nature that actually couples in this fashion? So, of course, we already said that spin 1/2 is just QED. Spin 1 is the electroweak coupling. So, what about spin 3/2 and beyond? But the problem, of course, is we know that there's no elementary particles beyond massive, in the isolated elementary particle beyond spin 2. So, but we actually have an interaction here. So, what actually corresponds to that? To answer this question, we can go back to the whirl line action, which all the couplings are now just given in terms of this Wilson coefficients. And we can take our minimal coupling and match onto this whirl line action. And if you do that, then you'll find that the corresponding Wilson coefficient will be given by 1 plus these extra factors that are suppressed by spins. So that means that if you take the large spin limit, which you can do by which we correspond to the classical spin limit in the sense that you take s to infinity, h bar to 0 with s to the h bar fixed, then this gives you exactly the CS equal to 1, which is the Wilson coefficient for black hole. And actually, the story becomes much more interesting when you consider the physical observables or to consider a scattering process. So equipped with this on-shell way of parameterizing this whirl line action, we can write down the general 3-point amplitude, which is for arbitrary Wilson coefficients. And so, for example, the 1 p.m. potential will just corresponds to this exchange of a single graviton line. And so since we're looking at the long range effect, so we're taking q squared, the exchange momentum q squared to be 0. And then the scattering amplitude just is given by the product of the 3-point amplitude, which is given by this generating function. Now, of course, this is not the final answer because the polarization vectors, the polarization tensor themselves carry spin effect. Essentially, epsilon, for example, here epsilon 1 and epsilon 2, they carry little group indices of different spaces, and these two spaces are related by Lorentz boost. So there's this extra effect, and to have a canonical version of parameterizing or setting up the coordinate system would be that we just take a reference momentum, let me call it P0. You can identify that with the center of mass momentum and set my little group space there. Then all the other spaces are just related by the Lorentz boost as GPP0. So then anything that is sandwiched between an in and out state of the polarization tensor will have a series of Lorentz boosts sandwiched between them. And this is basically nothing but the Thomas-Wigner rotation. And in this language, in this on-shell language, the Thomas-Wigner rotation, you can just write it out explicitly, which is a very simple form, this U factor here. So you have a UA and a UB for the two particles. So once you add this factor, and then you have the complete 1 p.m. potential to all orders, and you can just expand to any order you want for any general coupling. So the coupling comes in to this generating function. So we've been able to match some of the existing results that are in the literature. But this compact formula gives you basically anything to all orders that you might be interested in. If you set C equals to 1, then the generating function basically exponentiates, and then you get the complete 1 p.m. Kerr black hole potential that Justin derived. So since this Thomas-Wigner rotation is important, we can go back to the matching of the Wilson coefficients. And so previously we were just directly matching it back to the world line action. But now we know that we need to take into effect the fact that when we sandwich between two polarization tensors, we have this extra rotation effect. So instead of just matching back to C, we define what is called C effective. Just call C effective. And so basically CF effective is given by a linear combination of the original Wilson coefficients that we were matching to. And when you put these two together, you find that actually from the C effective point of view, the minimal coupling is exactly gives Wilson coefficient 1 precisely. So in other words, the minimally coupled higher spin particles do exist, and they are Kerr black holes. Okay, great. So now we've identified minimal coupling as Kerr black holes. So what does it actually tell us about Kerr? Well, for one thing, it tells us of some familiar stories that we've learned before. So remember, since by minimal coupling, I'm talking about just this X amplitude, X sandwiched multiplied by the spin factor. So if I just have X, then this will be minimally electrically coupled. If I have X squared, then this will be gravitationally coupled. So that means that minimal coupling corresponds to is relating two different objects by a double copy relation. So if there's something minimally coupled in the gravitational sense, for example, a Kerr black hole, then it corresponds to a double copy of something that was electrically coupled. And indeed, this was found by our friend long ago, Ricardo, Donald, and Chris, that in the Kerr-Shell form, if you write the Kerr metric in the Kerr-Shell form, which was already discussed earlier, you write it as a flat metric plus two null vectors multiplied by a scalar function. If you just take a single copy of this null vector multiplied by the scalar function, you will get a solution to the Maxwell equation. So this relates short-shell solution to Coulomb potential, and the Kerr solution to a rotating charge disk with the radius given by the spin vector. And so this non-perturbative relation is actually reflected perturbatively in this on-shell form in a very simple way, just by x going to x squared. Now, furthermore, this also tells us that the spin associated with this object that is minimally coupled is completely intrinsic, because it's obvious that the only thing that has spin in here is just the two spinner brackets. So the 2' to 2, these corresponds to incoming and outgoing momentum. And since the outgoing momentum is just given by a Lorentz boost to the incoming, so the 2' bracket is given by the 2 bracket times the Lorentz rotation. The Lorentz rotation can be derived kinematically. And so if you plug this in, then the 2 bracket is just given by identity, where this identity is an operation in the SU2 spin space, plus this extra factor, which you can immediately identify as the null momentum dotted into the spin vector, where the spin vector is just the Pauli-Lubensky spin vector. So putting everything together, then you see that it's just this, in terms of these spin operators or spin matrix, then it's just Q bar times S divided by 2. The big S is the classical, or the spin. So if you take S to infinity, then this essentially exponentiates, and then you see that the spin effect is just an exponential factor, where it's just Q bar dot A, where A is the spin vector normalized by the mass. So what does this tell us? Well, this tells us that to go from a Schwarzschild solution to a Kerr solution, you just have this exponentiation factor. To see its effect, we can look at the physical observable. So for example, we can look at the impulse, which is given by the 4-point at tree level is given by the, or at leading G, at leading 1 p.m. level is given by the tree level 4-point amplitude, exchanging again a single graviton, taking the Q squared to the 0 limit, and integrating over Q and Fourier transforming into an impact parameter space. So we already know what the 4-point amplitude is. It's just a product of 3-point amplitudes. And since the difference between Schwarzschild and Kerr is just this exponentiation factor, so that means that the difference is basically a shift in the impact parameter space, that it shifts the impact parameter by an imaginary value. And this is precisely the mysterious JANIS-NEWMAN shift, which was found long ago when, not soon after Kerr wrote down his solution. And JANIS and NEWMAN found that if you look at, once again, the metric in the Schwarzschild form, you can compare the scalar function for Schwarzschild and the scalar function for Kerr. You'll notice that the scalar function for Kerr is basically just a complex shift of the scalar function for Schwarzschild. So you just rewrite the Schwarzschild in this complex way, and then you just do a complex shift, and then you immediately derive the Kerr scalar function. So it was a mysterious relation found at the time, and this relation, and in some sense, it's really coordinate dependence because you really have to put things into this frame to look at it. And it's also not clear that doing this shift should generate a solution to Einstein's equation from one solution to another, but somehow it worked. It was slightly mysterious. But now we see exactly why it works, or why something like this should happen, is because of and if you look at things in an on-shell way, then the spin effect is just basically a shift in impact parameter space. So this is an on-shell version, a statement of that shift. Okay, great. So we've seen that the exponentiation factor brings you from Schwarzschild to Kerr. So now we can start going crazy. Let's just think, what else can we do with this X? So we would like to modify X by some scalar factor. Now this scalar factor has to be just defined through the objects that you have and hand, these kinematics of the 3-point interaction. So you only have Q, which is this massless momentum, P, which is the difference between the incoming and outgoing momentum, and you have the spin vector. However, these already satisfy P dot Q and P dot S is equal to 0. And so really the non-zero thing is just Q dot S, and we already have that. And so the only thing left is just a constant phase. That's the only thing that you could possibly do to this X. And we already heard from Donald's talk that this complex in the electromagnetic case, electric coupling case, that you're doing this constant, phase shift goes from an electric charge to a dion. So that means that there will, through the double copy relation, that should tell us that there's also a similar thing that is waiting for us, that if you just do this shift to the gravitational coupling, this just generates something new. And as it turns out, this something new, or the double copy of the dion, is the top-notch solution. So just to see some evidence for this, so let's list, so here I present the dion impulse, so we look at physical observables. So the dion impulse is given in this form, which is again, once the gluing of the 3-point amplitude, and this omega here is the rapidity. Okay, so the claim is that double copy should give the impulse for something that is probing a top-knot background. So by double copy, we mean that the phase rotation is square, and also there's going to be effect of the rapidity. And in the end, you get the double copy, you get this form where the rapidity is just changed to 2 omega. So this is the prediction from this phase rotation. We can directly match it to the usual GR computation, which is what you do is you just take the top-knot metric, expand to 1 p.m., you get the metric, the 1 p.m., the leading components, you convert it into the Christoffel symbols, and then you just write down the geodesic equation. Now, what is nice is that the geodesic equation in this way writing, you can just rewrite it in a Lorentz force form. The only difference with the usual Lorentz force is that you have these extra factors here, which in the end, you can translate into ratios of rapidity. So there's a ratio of cos 2 omega over cos omega. So these are the extra factor that you get. But because this is a Lorentz force equation, so all you need to do is take the dion impulse that I computed before and just rescale it by these cos ratios. And if you do the rescaling, then you immediately, obviously, that you just go from the dion impulse directly into the double copy result. And so this shows that indeed the double copy of this phase rotation gives you the top knot result, which we're computing here, a probe particle going through the top knot. Good. So the double copy of dion, we've showed evidence that this is top knot. Then this immediately tells us, just follow the original story, this immediately tells us two things. One is that there must be a complex shift that relates Schwarzschild metric to top knot. And furthermore, this complex shift must have some sort of electromagnetic duality correspondence associated with it. So there must be some kind of electromagnetic charge. So what is that? Now, for the complex shift, it's already known also soon after JANIS NEWMAN wrote down the complex shift that the Tobal generalized that complex shift and showed that this complex shift, there's also the corresponding complex shift that you can do to shift from a Schwarzschild to top knot. Now, instead of doing it in this way, we're going to instead translate this to this shift as a BMS super translation. And the reason that we want to do this will be apparent soon. So just a quick review of what BMS symmetry is. So if we have something that is asymptotically flat, then at the future boundary, you can write the metric in this form where U is the retarded time, gamma ZZ bar is the metric for the two sphere. And basically the whole thing is just controlled by the CZZ function. So for flat Minkowski space, CZZ will be 0. Now this metric is invariant under what is called a BMS translation, where the action is given here because CF here. So there's derivatives on U and derivatives on Z and Z bar, and also derivatives on R. And this action, this transformation is controlled by a function that is F, called F here. So for real F, the BMS translation is really a symmetry of this metric, and the associated charge is this T charge here, which is the super translation charge. Now, so first of all, one can show, so this was showed by a work last year by Ulrico and Massimo Parati, that the top knot metric is actually, you can actually get the top knot metric from this BMS translation. So instead of using, as I mentioned, since the real F corresponds to a symmetry, then imaginary F is no longer a symmetry, it generates something new. And they showed that if you do this imaginary F translation, then you will go from the Schwarzschild metric to the top knot metric, generating the C function here. Now using this, we've identified that if you take also this imaginary shift and act on the charges, and since we already identified that this shift relates Schwarzschild to top knot, if you act on the charges, then you exactly see that this generates the electromagnetic transformation, where the electric charge was the original super translation charge, and the magnetic charge is the dual super translation charge, which I give as in terms of M, so that is given as a function that acts on the C. So since we already know what the F function is, you can use this F to derive the transformation and act on the super translation charge, and you see that the super translation charge is being shifted by this rotation. And the shifted amount is exactly the top knot magnetic charge. So in other words, when we see on shell, it's just a trivial phase rotation. When you cast in this form, we can identify this phase rotation as a rotation between the translate from the super translation charge to super translation plus the magnetic part. Okay, so in this sense, we have in some sense, a complete characterization of all possible black hole solutions in just the 3-point amplitude. So, for example, the Schwarzschild is just the X coupled to the gravitationally coupled X. A rise to Nordstrom just means that it carries the electric charge, so there's X coupled to the photon as well. For Kerr, it's the spinning, this X stressed with the exponential spin factor. For Kerr-Newman, the electric coupling is also attached with this extra spin factor. And now we have the top knot. And finally, the final thing you can have is put in an exponential spin and an exponential phase, which should correspond to Kerr top knot, which is an ongoing work that should come out soon. Okay, now, good. So coming back to minimal coupling. So as I mentioned before, we have that these G minus, so going beyond minimum coupling corresponds to anomalous moments. So you might ask that, okay, so we see that these classical interactions are for black holes, these are given by minimal coupling. Are these extra couplings actually generated at one loop or higher loop level, just as the usual QED, the well-known story in the textbook, the G minus 2 in QED. Now, before we do any computation, we already know that G1, if I replace this x with x squared, we already know that G1 should be 0. Because there's two ways to see this. One is that if you think about local operators, there's actually nothing we can write down for G1. If you want to talk about things on shell, you can assume that there's G1, but then you can see that factorization cannot be consistent at 4 points. So G1 has to be a 0. A side comment of that is that if you have some double copy relation that double copies the electric objects to a gravitational object, the fact that G1 has to be 0 on the gravitational side tells you that G minus 2 has to be 0 on the electric side, which can be checked for the perturber string spectrum. So the question, so we should see that G1 is 0. So is it indeed 0 if you compute things on shell? And furthermore, what about the other G's? So we can start with spin 1/2. And the relevant diagrams are here. So these are all graviton, the wavy lines are all graviton lines. And we just subtracted out the G1. So individual diagrams, of course, is G1 is UV divergence and with actually finite pieces. And all of this adds up to 0, which is non-trivial, but is expected by, as I mentioned, that there's no operator that you can write down. Now for G1 and G2, for spin 1, you do the same thing and you find the spin 1, G1 is 0, but interestingly, G2 is not 0. So this is actually kind of interesting. So, well, first of all, the statement is that now quantum mechanically, you actually get corrections. And now you start to have anomalous moments at G2. Furthermore, it's actually finite. So it's also slightly surprising. And we don't have a good explanation for why that is finite. In principle, since at this order, in principle, you could have written, if I consider the spin 1 as a photon, then in principle, I could have written down RFF, for example, which would be, of course, that thing doesn't have a cut, so it shouldn't be running. But at least in an operator sense, it should be there. But I mean, so the explicit computation will show that it's actually finite. It'll be interesting to understand what this actually means, or it means anything at all in terms of these classical scattering. We're a little bit worried because we can put back in the scale factor. So here the statement is that, so for example, from the spin 1 computation, if you can include these diagrams, the minimal coupling will, of course, will have UV divergence. So the minimal coupling will be normalized. So, but the UV divergent part is weighted by m squared over m Planck square, and it has UV divergence. So potentially you have counter terms that you can do the matching. But because there's nothing at tree level and there's no UV divergence, so you just basically have a complete finite piece which is weighted by m squared over m Planck square. If you put it in that whirl line action, if I just naively put that in, this function, of course, this m squared over m Planck factor, of course, is small, for elementary particles, but if you put in a black hole mass here, this is going to be ridiculously large. So of course we don't expect this effect to be there, but it'll be good to understand what is actually, I mean, in which sense these should not be present in the considerations. Okay, so finally, but I guess I only have 2 minutes. And let me just briefly mention that there's also some interest. So as I mentioned in the beginning, that there's also another question about what would be the physical principle that selects these minimal couplings. And one of the things that you can ask, since this is a scattering process that involves spins, so you can talk about entanglement in the spin space. So it's really transition between different spin states. And so, so for example, if you have an in states that is given by the different configurations of the incoming spins, and then S matrix basically acts on the in states and gives you the out state. And so the different helicity, different spin configuration then gives you the different out space configurations. And you can do the usual thing, just naively just do the trace and trace out the von Neumann and get the reduced density matrix and then compute the von Neumann entropy. And the von Neumann entropy tells you the entanglement of the system. And so if you look at the minimal coupling, so this is a plot of the entanglement entropy that you will get as a function of the angle. So if you go all the way to, you'll see that it actually saturates the spin, the log 2. which is the maximal entangle. So this is for spin 1/2. This is for gravitational coupling. You'll see the same thing for minimal coupling for electric couplings. And you can start to think about if I turn on local operators. If you turn on local operators, you actually see that this maximal value starts to come down. So this is something that you can look at and perhaps as a principle to further guide our intuition about what, for example, the Compton amplitude issue that was mentioned before in Justin's talk. But this is something that is still ongoing. Okay, so I think my time is up. So in summary, we see that in terms of this on-shelf basis, properties of these black hole solutions are cleanly captured. Basically, they're kinematically minimal. And the simplicity of this on-shelf basis is also reflected in all of these hidden relations for the classical solutions, including the double Copley complex shifts and duality transformations. And even though all of these are really perturbative, the relations that they reflect are actually non-perturbative relations. And so this is a very interesting approach. And so I guess I'll just stop here. Thanks.
Okay, thank you, Yutin. Here's an applause for you. Let's see if there are any questions. Cliff?
Yeah, hi. Thanks, Yutin, for that nice talk. This fact that you can basically perform a complex shift on the impact parameter to get the spin is pretty fascinating. So I guess the fact that it comes from JANIS NEWMAN basically tells you that anything you can extract from the test particle limit will kind of have this nice feature. Can you comment on whether you expect this feature to hold at higher post-Minkowskian orders where you can't extract that data from test particle? Like higher loop. Let's say we went to very high loop.
Well, I mean, one of the things that you know I mean, that's exactly the point that Justin was making. And as soon as you go to one loop, these 3-point amplitude is not enough. So that means that you need to have to properly do the two. For example, the 2 p.m. results, you need to have these comptons handy. So
sure,
yeah,
but I guess I'm asking whether the simple replacement might still work. I understand that the amplitudes themselves don't, but could it be true that the replacement is still true?
So
or is that too much to add?
I think so. One of the things that so if it can be done, then that has to. I would suppose that has to mean that this exponentiation that happens at the 3-point is further still true at the 4-point level. Sorry, at the Compton, and therefore then induced at the 2-loop level, and that would mean that you're actually using the BCFW result for the Compton, which is non-local in amplitude space. But I think that Compton, if you actually use the BCFW, then that will be related by a complex shift because of the fact that it's just a product with 2 3-points. But so the question is then whether or not doing that is correct or not.
Yeah, whether it agrees with the right answer.
Yeah.
So we had, I think the next question was from Julio. Please unmute yourself.
So Yutin, can you repeat again what was a counter term that didn't have a divergence? So you found that there was the divergence canceled, and you said that there was an allowed counter term. What is the counter term?
I mean, if I would just, so at that order, right, in terms, of course, okay, so there's 2 things I can say. So first is, so this is 1 loop, and this is a graviton with two vectors. So obviously you can write down RFF. If I just consider the F to be mass, I mean, it has the right dimension there. Of course, we know that there's this divergence is actually not there in terms of the masses because there's no cut. Because if you want to cut RFF, you can look at, it has vanishing. The Helicity selection rule tells you that the masses part shouldn't have a divergence.
Okay, so there is an explanation.
Yeah, but here this is an operator. As an operator, it has something there, and this is and once again, this is massive loop. So the helicity, I haven't really looked at maybe the angular momentum that you guys are doing can actually tell us why it's not there's no UV divergence.
So Cliff, you still have your hand raised. I don't know if you want to add another question.
Oh no, I just have to lower it, I guess.
Okay, so then Alfredo, please.
Hey, thanks. So just a follow-up question to Cliff. So we understand how to construct the multiple expansion for the Compton amplitude, right? So that gives us the 2 p.m. We can construct the 2 p.m. scattering angle. So how about, and we sort of know it acts like some exponentiation. Right. But how about this phase shift? So how would you include the magnetic charge at 2 p.m.?
Oh, the phase shift for the.
Yeah. So how would you include the duality transformation when you're just in a two-body case?
If in a sense, if I'm following exactly what you did with the spin, then this would be that you just take the phase shift of the 3 point, and then you do the BCFW.
Right.
The necessary thing for the
but there might be contact terms, right, which should also be shifted.
Right. So, oh, I see. So you're asking me, how do I shift the contact terms?
Yes.
How do I identify? Yeah, that. I mean, but there's also the contact term ambiguity with the spin part.
Yes. Yes,
so
but yeah.
Yeah. So these are at the same level, which we need some new principles. Perhaps good if the good high energy behavior is sufficient to nail one particular combination down or something like that.
Right. So maybe self-force computation at 2 p.m. or something that could tell you how to modify the couplings, right, to include this magnetic charge. So I had another question. Maybe I didn't understand the last part about this entangled state at spin 1/2.
Okay, sure.
So you said that the entanglement entropy, right? So you can.
The von Neumann entropy, yeah.
Yeah, sorry. The von Neumann entropy happens to be critical for minimal coupling, right?
Right, but that's only for, because so this is an angle plot with a scattering angle. So of course the scattering matrix has different angles. So this is the von Neumann entropy is a function of the scattering angle.
Yeah, so I was just wondering what is this minimal coupling at the because you're considering a spin 1/2, right? So G1 is fixed.
Okay, good. So I'm comparing that to an operator that I could have added there, which is just the contact term. So like a 4 Fermi contact term. Comparing that to. So if I add in 4 Fermi contact term, and then this starts to come down.
So you're assuming minimal coupling to be not non-contact term interactions.
Yeah.
Okay. Okay. Cool.
All right. We have many questions. Actually, Andy Strominger has been raising his hand on the camera. I should again just remind you that you have this raise your hand option, on Zoom, which is easy to keep track of. But Andy, are you still with? Are you here? Could you ask your question now, please?
Sorry, I can't seem to find it. I'm sorry. I have two questions. What happened to the spin to mass ratio? How does that go into the formalism?
Oh, it's this right. This A. Right. So naturally, what we have is so these A's are spin to mass.
I'm sorry, I didn't see A's in your right there in the metric, but in your Are you able in this formalism to discuss things with spin greater than mass squared? Does anything special happen when at the extremal point?
At this level, we don't really see, and that limit, we don't expect this formalism to be actually correct. It's not really valid in that regime. And this was also discussed in Justin's talk. If you can naively analytic continue it, but if we in this form, if you naively continue it, we don't really see anything wrong at this level. But we don't expect, it's already outside the validity of this approach because we're doing a gene expansion.
I see. So, so you're assuming the spin is much less than the mass.
Yeah, or the validity of this approach. Yeah.
And also, I mean, if you throw something at a black hole when they interact, a salient feature is you excite a quasi-normal mode, and that will have some exponentially decaying waveform that goes off. That is also outside the regime of validity of this. That's also a phenomenon that's not seen in this approach? Or
it would be like, I would say that there will be something that is another class of 3-point amplitudes that we will be considering. So here the 3-point amplitudes are just, are the same mass and a photon and the massless particle interaction. For those cases, you would look at different masses because they're different black hole states. incoming and then emitting a graviton, and so you'll look at different mass interactions. And it's well known that those interactions are actually a separate class of interactions that do not have a smooth equal mass limit. They don't just go back down to minimal coupling. So those will be, yeah, those are also things that people are looking at, and we're also interested in how do you write down the on-shell version of this quasi-normal modes interaction, but they're not included in here.
I see.
All right, we're running a little bit over time, but I think it's fine to have the discussion. Maybe a last question from Chia Shen, who cannot raise his hand because he's co-host.
Oh, thank you. Yeah, so I just have a quick question about the Kershaw solution that you found. So obviously those solution correspond to the nice 3-point amplitude. But I wonder if there's anything special for that space-time as well, other than the 3-point amplitude.
Sorry, what do you mean by space-time?
I mean the space-time solution.
In the class?
Yeah, of course, it nicely corresponds to the 3-point amplitude, but other than that, it's not anything else that's very special for that space-time solution. Maybe, for example, the quasi-normal mode would be simple, something like that. I don't know.
You mean the classical? Oh, you mean what else looks simple in the Kershaw form? Is that?
Yeah.
What?
Yes.
I'm not actually. Well, I mean, maybe one of the things is this shift relation, right? I think there's also many other things that are manifest, but yeah, like one of the things I'm familiar is the shift relation.
Okay, thank you.
Okay.
All right, thanks very much, Yutin, and applause to you.
Thank you.